Hi there. I want to deal with a few things related to topics 1, 2, and 3. The first thing I want to talk about is what an electroscope is. Here's a little device that would be like an electroscope. How does it work like an electroscope? If you take an object and you charge it up, and then you attach that object, like you see here, to the top of the electroscope, depending. So in this case, or this example, the charged object might have negative on the end. If that is the case, what happens is the positive charges of the metals in the electroscope will come up the rod and be attracted to the negative, and it polarizes. So all the negative goes to the bottom, and the two little leaves will pull apart if the object is, in fact, electrostatically charged. So what happens when you remove the charged object? The leaves go back together. So that's how an electroscope works. Again, when we look at the electroscope, we know it's charged because the two little leaves will go apart. Next, let's look at, here it is again, so these two little leaves would go apart. Let's see if we can fill in the blank for this. The farther apart these two little leaves go, the stronger the electrostatic charge. Let's fill in the blank. Use this list of words. Charges are unlike. That would be opposite. Two like charges are either both positive or both negative. If two blank charges are brought together, they will experience a force of attraction. If two opposite charges, if a blank charged balloon is brought near a positively charged rod, the balloon is attracted. So this should be negative. A piece of plastic has no charge on it. This means that it has the same number of protons and electrons. Okay, so let's leave the electrostatic and let's talk about the triboelectric effect. So the triboelectric effect is also about static electricity. When you rub two materials together, one will pick up electrons and of course the other will lose electrons. Different substances have different abilities to do that. So asbestos and glass and nylon are really high on the triboelectric series, which means they tend to lose electrons really well. However, silicon, rubber, Teflon, they tend to accept electrons really well and therefore are really low. And so the best device would be one that we took something high here and we rubbed it against something low here. So rub silicon rubber with asbestos and you will get a really, really good static charge out of it. Next, let's deal with practicing some of Ohm's law. So practicing some of Ohm's law. If you remember, and we're going to try this practice test too. So let's just pull up Ohm's law for a minute. So there are three versions of Ohm's law we need to know. Voltage is equal to current times resistance, or current is equal to voltage divided by resistance, or resistance is equal to voltage divided by current. So let's try some practice problems. So voltage is equal to resistance, times current. Pull this back up. An automobile has a resistor of 24 ohms. Car batteries provide 12 volts. Calculate how much current. So we have to change this. Current is equal to voltage divided by resistance. So 12 volts divided by 24 ohms, and that should give us our current. So what would that be? 0.5 amps, capital A for amps. So that's an example of that. Next, let's try a practice quiz. My practice quiz is right here. Let's make it a little bigger to see. If you comb your hair on a cold, dry winter's day, your hair tends to stand on end because, well, what happens is electrostatics works really well or much better with dry conditions. The more moisture in the air, the less chance there is of building up an electrostatic charge. So why does your hair stand on end? Each separate hair has a opposite charges, and so it would be B. The unit used to measure electrical current flow is the amp. Okay, the joule is for energy, so it's not the joule. A unit used to measure potential difference or voltage is, that's an easy one, that's the volt. Next. It says if the resistance of a conductor is 98 ohms and 26 volts, what's the current? So we know, let's erase this. We know that voltage is current times resistance. So what do we want? In this case, we're looking for voltage. So that's current times resistance. I times R. So we're looking for current. So current is voltage divided by resistance, which means 2.6 divided by 98 ohms. And so 2.6 over 98 is A, 0.027. Want to double check? We can double check with the calculator.
Two decimal 6 divided by 9.8 equals 0.02653061224489796. Clear.
There you go. Next, a voltmeter connected to an electrical bell rings 3 volts and an ammeter in series with the bell reads 0.2. The resistance is Okay, so let's again use our formulas. So let's grab this. So what are we trying to find out? The resistance. So what is resistance equal to? Resistance equals voltage divided by current. And so the voltage is 3 volts and the current is 0.75 amps. So 3.0 volts divided by 0.75 amps. So this is V for volts, A for amps. Let's get our calculator out again.
Clear, 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 clear. 3 divided by decimal 7.5 equals 4.
Okay, so the answer is D, 4. Electrical circuits that have more than one path are called what? Those are called parallel circuits. So it says let's consider 4 small spheres, A, B, C, D. Sphere B is positively charged. B attracts to A, so A's probably got to be negative. C pushes away D, so they have to be the same charge. Okay, so let's write down what we know. So according to this, B has to be positively charged and A has to be negatively charged because A and B attract each other. C and D have to be the same charges. A repels C, so that means C has to be negative because they are the same if they repel, which means D has to be negative. Okay, so B is positive, A is negative, C is negative, and D is negative. The law of charges comes in 3 parts. Fill in the blank. Unlike charges attract, so positives and negatives attract, like repel, and a neutral object will attract to a positive or negative. That's the third thing. It says make a circuit to show a cell connected in series with a switch, a lamp, and an ammeter. Let's erase. We have circuit symbols that we need to use to do this. So it wants me to draw a cell. So let me do that for you. So electrochemical cell, there's the positive and negative. Okay, that's a positive component to the cell. And there's the negative part to the cell. That's the negative terminal. Next, let's draw a line to represent the wire. It wants me to draw a lamp. So there's a lamp right there. An ammeter. Now it's important to understand how you hook up an ammeter versus a voltmeter. Ammeters are connected in series, not in parallel. So I draw a circle with an A, and that's my symbol for ammeter, and it's connected as part of the circuit. And I need to also draw a switch somewhere along here. So do this. And it's all in series. I need to show electron flow. Electrons flow from negative to the positive terminal. So there's my electron flow around the circuit this way back to the positive terminal. And so that's how